So some of the people in the room, including Dick, have seen these slides several times because this was our promise. But we were already working on these issues, and so behind the scenes there was some actual research going on. And so the rest of the talk after the big data is a real phenomenon. We'll talk a little about what the phenomenon is. But the intellectual fact on the ground is that if you don't bring together sophisticated computational ideas and sophisticated statistical thinking, you're not going to make progress on this problem. So it forces us to bring computations. There could have been other ways that computations and statistics were brought together, but this one is really forcing us to bring them together. Okay. All right, so I've turned on streaming video. If there are people in the outside world, welcome to you. So let's talk a little bit about what this phenomenon is. I don't really have to say that much about it. All of you read the newspaper, and I've seen all the hype about this in Silicon Valley and other places. But let's also talk about not just the technology side, but the science side, because this really probably was where it first came from. So big science has generated and is generating huge amounts of data. And there are two reasons that the data are being generated. I like to think of them as confirmatory and exploratory, kind of in statistician language. So confirmatory is kind of the classical hypothesis test. There's a standard model which describes the world, which is probably a little bit wrong, but it's a pretty good model. And you want to test that against some alternative, that there's some thing you missed in your model which is now present, say a Higgs boson. Okay? And the difference between the null and the alternative is really almost nothing, because if it would have been a big difference, you would have seen it before. It's going to be some little small difference. In particular, under the standard model, there's some density function for some physics entity of some kind that you could calculate with huge amounts of simulation. That's actually how it was done. You couldn't calculate it, but you simulated it for forever and forever. And you got some kind of a density function. And the alternative was exactly that same density function with a tiny little blip somewhere. And you wanted to test, is that blip really present, given that everything is all these things are random objects, these density functions. And so to get that difference to be reliable, so that your test was real, you had low error rates. If you were to do this test many times, it's kind of a funny concept, but that's the thinking. You had to gather huge amounts of data to reveal the signal. The signal difference is really small, so you had to gather huge amounts of data. And moreover, there are energy regimes which haven't been explored before. So that also just generates subsidiary data of some kind to just get up into that energy regime. All right, so this is still happening in physics. You're trying to test hypotheses, and you have to gather huge amounts of data to test hypotheses. That's confirmatory. The more common way to generate big data is exploratory. So astronomy is a good example. You just collect all the data you can about the universe, and hopefully new things will arise. That's kind of what astronomers often do. Genomics is another example. You just collect the entire genomes of all kinds of species and all kinds of cells inside of species and hope that new things will emerge. All right, so that's exploratory. Statistically, the error control is very different here. It's not type 1, type 2 errors in a null and alternative. It's that I found a whole bunch of stuff as I was scanning through all of my data. Of that stuff, what fraction of it is complete noise and what fraction of it is real stuff that I should explore further? Okay, very different statistical control needs to be exerted in that case than in the confirmatory case. Okay, so we'll get into this a little more as we go. The second one is the one I think more of us are more familiar with, the internet, measuring data, all of our click streams, all kinds of information about us is being gathered, and the data is getting bigger and bigger and bigger. Now, what's interesting about the data getting bigger and bigger and bigger isn't just the bigness. Okay, big data has been around for a long time. It's not just the number of bits and all that. That's not interesting. So one way to make it more interesting is to note that it's the granularity that matters. That's what really changed. So in the last 10 years, say for the internet, there's now data about most human beings on the internet somewhere, right? And more of the companies want to make inferences about each human being. They're not so interested in aggregates about typical people in San Francisco. They're interested in every single human being. When they come on their server, what are they going to click on? What can I sell them? What are they going to be interested in? Doctors are interested in doing personalized medicine for every single human being. They come in and you give a regime that's targeted for that individual. And so on and so forth. Every entity in many, many domains we care about, there's now enough data to start to say something about that entity inferentially. And you want your error rates to be small across all individuals. So that's, to me, what's really different. It's the granularity of the data. Now, that said, there's these long tails and so on and so forth. For 2 billion people, you have huge amounts of data, not even, maybe hundreds of thousands. And for the rest of them, you have a little bit of data. And your inferences are going to be unreliable for all those people. All right, so what do? Well, statisticians have answers to that. It's called hierarchical modeling. You shrink. So you don't have very much data about me, but I'm a very similar person to Alistair Sinclair, about whom you have lots of data. You take inferences about him and use them as a prior, in some sense, for me. Okay, so just a little bit of extra data is needed for me to get good inferences based on my similarity to other people. Of course, that similarity may not be known a priori. That's part of the inference problem itself, is to set up these models that set up hierarchies that allow information to flow. Okay, so that's what's new as well, is trying to build huge, vast hierarchical models in which you have billions of nodes, in which there's uncertainty throughout this thing. Okay. You start to see this evidence of this in the database literature, where databases classically, you put in a query, you got an answer. And the query had to do with what was in the data, period. There was no inferential idea. Or you're trying to query what's behind the data. That just wasn't present. But now you start to see the database people talking about more inferential ideas, and they're interested in, moreover, every query comes in, you give an answer with an error bar. Very brand new way of thinking for those people. Every query has an error bar. So you percolate that uncertainty around, and you worry about characterizing that error bar, and then having consistent sets of error bars across multiple queries. All right, so that's what statistical inference is about. Okay, so that's a little bit of background on what the phenomenon is. Let's just now leave the phenomenon high. We all aware there's big data, but let's particularly think about granularity issues. But what's the intellectual problem? So let's talk a little bit in computer science language. Here's one way to frame the problem and cast it, is that classical theory of computer science has been about the management of resources, time and space and energy. And you try to set up equations that relate these quantities. Each one of them has a symbol, and you write down a trade-off law that talks about how they trade off in some situation to solve some problem. In those equations, there hasn't been, data has not been one of those symbols. Data is the thing you apply the resources to. It's the stuff you move around. It's not viewed as desirable, less or more desirable to have more or less data per se. Okay? Now, if that has implications for the amount of memory you need and the amount of cycles you need, then yes, the equations apply to those quantities, but they don't apply to the quality of the data and the inferences you might get out. Okay? So, signal to noise ratio doesn't typically appear in a theoretical computer science equation. But what's new is exactly that we now need to talk about it as a resource. You may have to pay to get your data. You may need to pay to get more to get high quality data, especially out in the tails, and that may trade off against other constraints you have on your problem, particularly the runtime, the storage, and all the other issues that come up in classical CS theory. And one way to think about what's interesting about this problem that's really novel is that with most of those classical resources, there was kind of an obvious monotonicity. The more of it you had, the better. All right, the more memory you had, the better. The more cycles you had, the better. How could it be otherwise? And the equations of theoretical computer science would certainly reveal that monotonicity, and then they would do that in a much more quantitative, rich way. But you added a resource, the only things could only get better. That was sort of a minimal requirement. Now for data, that's just not currently the case. I think it actually has to be eventually the case. But if you certainly do consulting, you find that it's just not the case. That more data comes in, and you start seeing error rates get bigger and bigger and bigger. And so we have to think about a little bit what's happening there. So again, sort of using computer science language, let's think about data as a table. So there's rows and there's columns of the table. Rows are, say, individuals, people, and columns are descriptors of the people, say age, height, weight, income, so on. So classical database might have 10,000, 100,000 people in it, and the number of columns is kind of the number of distinctions you need to make among the individuals in your database. So, if there's 10,000 people, maybe age, height, weight, income, and so on is enough to sort of say interesting things about the people in the database. Now, if the database not suddenly has 3 billion people in it, which lots of modern databases do, a few dozens of columns isn't enough anymore to make all the distinctions you care about. I'm going to start caring about more granular things. I care about, what's your favorite food? Do you ride a bicycle or not? What book did you read yesterday? What's your genome? What's the 500,000 important markers in your genome? And so on and so forth. I'm going to have all kinds of descriptors I'm interested in, try to get inferences about individual people for issues I care about, say their health or their buying patterns or so on and so forth. So roughly speaking, this is no theorem, but you might imagine as I collect more and more rows that the number of columns has kind of got to go linearly. It's got to somehow expand in some related way. And now the statistical problem is that the inferences I'm trying to make are in the language of combinations of the columns. I'm not going to be interested in just if you eat a certain kind of food, will you click on my ad or not? It'll be if you eat this food and you live in San Francisco and you bike to work and so on. We look at combinations of the columns and use them to make good predictors of some outcome I care about, say health or buying patterns or clicking patterns or whatever. All right, now we're theoreticians. We know that the number of combinations of columns goes exponentially in the number of columns. So if the number of columns is going linearly, the number of rows, the number of data points, the number of hypotheses we're willing to entertain as we get more and more data is going exponentially in the number of data. Okay, that's problematic. Because you're now going to find, for sure, lots and lots of combinations of columns which will match any pattern you care about as we get bigger and bigger data. And almost all those combinations will be complete noise. Right? They'll just be random fluctuations. They won't be true of the future. All right? You see this in companies. They will start gathering data, and as they start gathering data, they will start asking more questions, willing to look at more stuff, be more ambitious. That's the whole point of gathering the data. But they don't realize their ambition is really exponential ambition. And so they start gathering more data and they start seeing the error rates going up, and people are all getting concerned about this. All right, now in some sense we know how to solve some of these problems at least. Statistical theory talks about family-wise error rates and control of fractions of false positives and so on and so forth. But all those procedures are themselves algorithms. They take a certain amount of time to run, and they may be too much on the scale of the data. You may have to not be able, you may not know how to do that, or you may have to approximate it in some way. We don't know how to do that. So it's still kind of open to do this. The fact is that you get more data, you start to see error rates often going up. Now, if you were just trying to infer one quantity, the mean of the data, the mean height of all people, and never ever try to be more ambitious, as you get more data, yeah, the error rate will go down. That's 1 over square root of the number of data points. All right, but that's not the perspective of modern data analysis. We're not trying to infer one thing as we get more and more data. We are typically allowing ourselves to be more ambitious. All right, the other side of the coin is more classically algorithmic, which is that all procedures for doing inference are algorithms of some kind. They are n cubed, they're n log n, they're n squared, they're maybe sublinear. And a lot of the energy in this topic of big data so far has been on trying to drive those rates down. Just kind of classical algorithmic thinking. How do we get, here's an algorithm of some kind, the lower bound, we don't know maybe, or it's quite low. Let's find an algorithm which does a better job. And this will go on and on and on. This is important. But now let's think about, in the context as we get more and more data, what those tools will allow us to do. So let's suppose I have an algorithm I really love. It's been analyzed to death. It's really a great algorithm, and it runs in type n cubed, and n is 10,000. And now I'm trying to solve my problem and get an inference in 10 milliseconds, or maybe a single millisecond. So I'm doing online auctions, right? So it needs to be in sub-millisecond range to have any hope to win the auction. All right, so 10,000 data points, in cubed, it's fine. I can do it. All right, but now I get more data, a million data points, and that n-cubed algorithm doesn't look so good. It won't finish in that millisecond. All right, more if I stop it halfway through, maybe it's not a kind of a nice online type algorithm. It'll give you a nonsense answer, or maybe it's even an online algorithm, but still, there's no guarantees anymore that it'll give me a good answer in that millisecond. So it's just not satisfying to stop an algorithm and say that's my answer, typically. All right. So what do you do in that situation? Now, of course, the data is still growing. A million, that's not very much. I'm getting a billion, and so on. I still have that millisecond boundary. Well, I could start dropping data, but now I need to know the rate at which to drop data. How many data points do I drop as a function of the time budget I have? To know how to do that, I need to know the amount that each data point contributes to the risk, because I'm trying to control the overall risk error rate. So you don't know that a priori. So you might start dropping data at some guessed rate, and as you're dropping data is streaming in, you're making your inference, and your error rate, unbeknownst to you, is going up and up and up, because you're dropping the data too quickly. The other thing you can do is start to back off to simpler algorithms. So n cubed, that's a great algorithm, but someone else knows a cheaper n squared algorithm, or maybe n log n, which gives a worse accuracy in an optimization sense, right? But's cheaper, and it can run on that data in that amount of time. So as your budget stays fixed, your data is increasing, you back off to a simpler algorithm. But your accuracy got worse, and so maybe your risk got worse too. Unless you can calibrate optimization accuracy against risk, again, your error rate could be going up as you're backing off to simpler and simpler algorithms. And a limit, of course, those kind of become the same. As you back off to a sublinear algorithm, you're basically dropping data. Okay, so those are real problems. This is kind of the state of the art. If you go in industry, you see error rates going up and they don't know how to deal with it. And so we as a community somehow need to face this. This is kind of very serious. We're not doing kind of the minimal thing, which is allowing data to come in. I got more of my data. I'm happier and happier and happier. I'm not more and more traumatized by the error rates. Here's one way to express an ultimate goal. There's many other ways to express this kind of thing, but here's one just to give an example. So given an inferential goal, that means, I'm going to talk about risk functions here in a minute, that means a risk or an error of some kind, and a fixed computational budget. If we didn't have that requirement, there would be nothing new here. We'd be back in classical statistical theory. Given an inferential goal and a fixed computational budget, provide a guarantee that the quality of inference will increase monotonically as data accrue without bound. And so without bound is really the computer scientist in me. There should be scale-free principles of some kind. We should have to solve this problem every generation at terabyte, exabyte, petabyte, whatever, et cetera. There should be some notion of scale-free principles that we can somehow discover so that we wouldn't have to solve this problem again and again and again every generation. Okay, so those are the slides that we presented at the Simons reverse site visits and so on and so forth, trying to compel people. There's a real problem here. It's intellectually deep and interesting, and by bringing together 100, the world's smartest young people, we'll solve these kind of problems. Okay, so I won't preview what's going to happen the rest of the semester. Hopefully, brand new things. But let me now do real boot camp kind of stuff. Let's now slow down and talk a little bit about some of the tools that at least I think we need to be able to have a language to talk about these issues. And so one of them, the main one, is going to be this notion of a risk function. So this really is Statistical Decision Theory 101. I'll go slowly here. This is what we teach in the first class in graduate level stat.
Just one quick question.
Yes, please.
Going back to the ultimate goal.
Yeah.
For given the space of all inferential goals, is it an argument that such a thing exists for some without a bound? It always exists, or
there's no argument that such a thing exists. So I want to, I give you kind of in the rest of this talk. There's a little domain where we have an example of solving that problem. But it's kind of based on upper bounds, and it's not so satisfying in some sense. So I think it's an open problem. I kind of throw it out there as we haven't solved that in any domain I'm aware of. Well, there's lots of related research to get at pieces of it, but it's sort of still open. Okay, so a little bit of decision theory. Apologies to the statisticians in the room. I'm going to be very elementary, talk about kind of a very restricted special case situation, but just get the vocabulary present, okay? So you can ask, well, can you handle this, this, and this? Let's just sort of not do that much of that and just try to understand the vocabulary so I can move quickly. So data is going to be called X. It's going to be random, so it's a capital letter. That could be a whole time series. It could be a graph. It could be it's data of some kind. There's going to be a probability model. There's a family of probability models for the data, and they're going to be indexed by something we'll call a parameter. Parameter doesn't have to be a fixed finite dimensional object. It could grow as the amount of data. It could be a function. It could be a measure. It doesn't have to be a finite dimensional Euclidean vector of some kind, but let's call it a parameter. So given the data, we're going to talk about an algorithm or procedure delta. It operates on the data, and it produces a decision. Now, we'd also, to set up decision theory, we need a loss function. It's a real valued functional of the parameter and the decision, so in some sense compares them. In the simplest cases, it just takes a difference in squares or something like that, but the 0, 1 losses do something else, and there's just huge numbers of loss functions out there. It's one of the most active areas in statistics, is to define clever new loss functions. So that's the loss function, and most statisticians of any stripe would agree that we need to talk about loss functions, and we need to have this function of two arguments. Something to do with what you're trying to infer, which is the unknown state of nature, and something to do with the data and your algorithm operating on the data. Those are the ingredients you need to talk about. There are two arguments to this function, and as I'm going to emphasize here in a second, that leads to two different approaches to statistics, Bayesian and frequentist, and there's only two. So, there's been many debates over the years whether there should be other approaches, and there's still kind of Fisher's fiducial inference laying around and so on. But really the field has decided there are two. It's kind of like waves and particles in physics. It's a pretty fundamental distinction. There are two approaches, and they're different, and they're complementary, but they are different. So it's one of the things, in computer science, there's kind of like two flavors of computer science. There's kind of one, and that's it. Statistics is in this sense more like physics. It's kind of an intellectual challenge to get used to this idea. There are two approaches. I'm going to try to give you the idea a little bit of why, one way of seeing how they both relate and how they differ. Okay, so this object here is a function of it's a mathematical object, but it's unknown in a real data analysis situation. You don't know the state of nature, that's what you're trying to infer, and this is random. Okay, so it's going to vary as you deploy this procedure in many situations. So if you were trying to figure out which procedure is better, Dick has a procedure, I have a procedure, which one's best? You'd like to compare their loss, right? But on which x? Well, it's random, so in some sense it should be an average over x that you would want to compare, or some other way of picking a particular x. So it's random, it's unknown in two ways, both arguments. All right, so here immediately we have a bifurcation in statistics. Which argument do you focus on to try to get this thing to actually be a number that you can compare? My procedure has value 4.5 and his has value 5.5. I'm better in terms of minimizing. All right, so the frequentist will focus on this argument first and hold this thing fixed. This is not known, but let's conceptually hold it fixed. Unknown, but fixed. And this argument is random, so let's get rid of the randomness by, in fact, taking an average. Okay, we want to be good over all the possible data you could see, not over this subset of the data, okay, or this particular regime. Okay, so the frequentist will take this object here and take an expectation over it, where this expectation is an expectation for a fixed value of one of the members of the probability family, for theta being fixed. And it's very critical that this is the same theta as here. Okay, you fix theta, you pin down the loss function at that value of theta. It's a stripe through the loss function, through the space. And that same theta is being used to define the probability model with respect to which you do the expectation. So this overall object is going to be a function of that single fixed theta. If you can plot it now as a function of theta. All right, this now is gone. That's been averaged over. X is now gone from this. It's just a function of theta. All right, so that's called the frequentist expectation, and this function now is called a risk function. And that's what most of us spend a lot of time, especially in the theoretical side, is trying to analyze as a particular risk function for a class of problems. The Bayesian, on the other hand, the other approach to statistics says, well, no, the data is fixed. You shouldn't be thinking about other data you could have gotten. In this particular data analysis problem, you got a particular set of data. That's X. Condition on that. Condition on that. And try to calculate some notion of error or risk conditioning on X. And now if X changed and you look at another X, you get another notion of risk or error for that X. So condition on X. You never try to average over X. And that really is the critical difference. Whenever you see it average over the sample space, over other data you could have gotten, you're being frequentist. You're saying, on a lot of kind of data, I put out a piece of software, and I want it to run on many data sets, and I want it to be good over all those data sets. That's a frequentist way of thinking. All right, the Bayesian says, no, don't look at other data you could have gotten. Try to calculate some notion of average for a specific data point. All right, so the Bayesian takes a different expectation. There's no sub theta here. This expectation is just a conditional expectation, where now what's random is this. Right? So the Bayesian has to have a notion of a probability distribution on the parameter. And that's where you immediately get into a notion of a prior probability. You have to have a probability distribution on the parameter to even define this expectation at all and make any progress. All right, from the very beginning. Okay, let's plot a risk function. A risk function, let me erase over here, is a function of theta, and so in the one-dimensional case at least we can make a little plot. Here's theta, and here's a kind of a typical risk function. There might be some regime where you do particularly well with this. This is for some procedure, procedure A. You do particularly well, and some other regime where you do not so well, typically. One way of thinking what the Bayesian is trying to do is the Bayesian is going to put a density on this theta and say there's some regions I care about the most. Okay, and then I can take an average with respect to that density and get a notion of risk, which is kind of favors certain regimes versus others. Okay, the frequentist is not willing to do that. They don't want to have to put this prior distribution on theta, and so they're stuck with talking about a whole function for procedure A and another function for procedure B and so on and so forth. Now, if procedures look like this, and so on, and there are many procedures, and they kind of look like this, they never crossed, then this framework would be just unassailable, be fantastic. You'd be able to say this procedure is just always better for all values of theta than this, so just kill this procedure off. It doesn't even belong in our list of possible procedures to consider. All right, that concept is called inadmissibility. This procedure is inadmissible with respect to this one. Or it's inadmissible, period, and here's the witness to that inadmissibility. All right, but typically, in fact, procedures look like this. There's some regime where they work better and some where they don't. All right, so you're a frequentist. You're now circa 1930s. Wald was sort of the first kind of statistical decision theory person. What do? You're not willing to put a distribution on theta where you could average over this and kind of collapse everything. You're stuck with this whole function. All right, so the ideas that were come up in the 30s still are alive to this day. There's sort of kind of three main ones we often teach. There are others, but they're kind of, you'll get the spirit just by talking about three of them. Let's get rid of this funny one here. The first thing you might do is you might constrain your class of procedures. I'm not going to look at all possible procedures. I'm going to constrain them. All right, so one way to constrain is to talk about unbiased procedures. I'll talk about bias here in a second, but I think you all kind of know what that means. So unbiased procedure, a special class of procedures. Maybe in that class of special procedure that you plot the risk functions, they do like this. All right, in fact, they do. And that's kind of a lot of the classical theory in the 40s and 50s was about best unbiased linear estimator, best unbiased this and that. And the classical texts are full of these things. And it's because the risk functions look like this. Okay? The problem was that class was not a very good or rich class. There were lots of things out of that class that had bias, which actually had much better risk. So you probably in real life wouldn't want to use a lot of these procedures. And in fact, nowadays, almost all estimators we use are biased procedures. It's better to allow a little bias. All right, but anyway, that was classically very important, still around to our day. Another thing to do is very much alive to our day is minimax. Okay? So what you do there, you all know, I think, is that you look over all theta and say maybe these guys top out here, that guy tops out there, so its maximum value is here. This guy may top out here, and its maximum value is here. And I take the minimum of the maxima. And I define a procedure which is minimax over theta. It's still very much alive to our day. And there's in fact a little bit of a duality between minimax and Bayesian. Because there is a worst prior which can concentrate all the prior mass on thetas which give you the worst possible behavior. And so the Bayesian expectation actually becomes the same as the frequentist expectation. Minimax is alive to our day. Another one is more kind of group theoretic. It's called equivariant estimation. If your probability models have a group theoretic structure, such that you can move around a space of parameters by a group operator, your estimator should have that same structure as well. Okay? You should have an isomorphism between your estimators and your model. And so you would restrict yourself to estimators which have that isomorphic structure. And then again, you might get this kind of nesting or layered structure, and you often do with equivariant estimators. Again, that's kind of an unassailable, nice approach. If that happened all the time, then we'd be done. It only happens in specialized problems. Okay, so that's a little bit on kind of the quandary that frequentist statisticians find themselves in. They're trying to take an expectation over delta. That's in some sense mathematically fine, easy to do. The Bayesian doesn't like this because they say, well, you're looking at other x's you could have gotten to help change your, to make your inference. You only got, other x's shouldn't change what you're doing on this x. And in fact, you can get into some quandaries that way, and that's kind of what Bayesians have emphasized. And then the Bayesian, on the other hand, takes the average over the theta. Okay, so I wanted to now do a little bit on the whiteboard here. Let's just take a couple of examples. So let's look at just kind of a 1D location parameter problem. So theta is just going to be a one-dimensional scalar value at this point. And let's call delta x, let's call that theta hat. Just change our notation. Theta hat is the standard notation used for point estimation. So delta x takes the data and puts it in the same space as the parameters so you can take compare them, take a difference. This is, of course, random. It's a function of the data. So it's just a different note. We left off the x of the notation, but it's clearly random. And then the loss that we're going to consider here is just theta is just going to be the square difference. So L2 norm. Okay, so that's the loss. It is in fact problematic because this is random and this is unknown. So you wouldn't be able to use this function per se to compare procedures. So you take an expectation, and we'll do a frequentist expectation. So R of theta is just equal to expectation with theta held fixed of this object. And now you apply to an old theorem by someone named Pythagoras. You turn this into these are squares, so you turn this into a little triangle and look at the two sides of the triangle. Okay? And so the way you do that is you just add and subtract a term. So let's put in here theta minus this constant minus theta hat minus that same constant. Square it. Okay? So that's just a constant, right? And now you square it out. And the first guy here is the expectation of theta minus this expectation, quantity squared. This guy over here is expectation of theta hat minus expectation of theta hat, quantity squared. And then there's a cross term. All right, and because this is Pythagorean, you might hope that the cross term vanishes, and indeed it does. It almost always vanishes in statistics. And to see that the cross term is going to vanish, you note that this is a constant, so that expectation can come past that. That's a constant, so that expectation can come all the way into here. Now when you hit this object, this becomes expectation of theta hat minus expectation of theta hat. It's 0. Okay, so this goes to 0, and we just have these two terms here. And those two terms have names. They're called the bias squared and the variance. So that's equal to the first term is in fact the bias squared. And let's drop the expectation now because in fact nothing inside those parentheses is random. Plus the variance. Okay, so bias squared and variance. All right, and so lots of sort of very classical elementary statistics starts with L2 and writes out the bias squared and variance. And so instead of trying to control the risk overall, you try to control the bias squared and the variance. So you typically will get a trade-off. Some tuning parameter in your algorithm will make the bias go up, but the variance go down, and you try to set that parameter to optimize the sum of the two. Classical unbiased estimation said the way we're going to optimize the sum of the two is we're going to set this to 0 and then try to minimize this. Okay, so not a very satisfying answer to the optimization problem in general. But this way of thinking of breaking this thing into these kinds of pieces goes much, much further. So this typically becomes known as the approximation error, and this becomes known as the estimation error. And you use all kinds of mathematical covering tools to study these objects. And empirical process theory is generally used to study this object, and approximation theory in mathematics is used to study this object. And again, you typically will reveal a trade-off. There'll be some parameters that you can tune in some algorithm, which will make this one go up and this one go down, or vice versa. And a lot of the mathematical analysis of many procedures, non-parametrics, high dimensional, and so on, is trying to calculate, approximate or calculate these kind of terms and then reveal the trade-offs inside them. Just maybe for the really to be really elementary, let's do this for the Gaussian. So let's say that that xi is coming from IID. I have n of them from a Gaussian with mean theta. So I goes from 1 to n. And then let's make our estimator be, it's a function of x, it's going to be the sum of xi, I equal 1 to n, the sample mean. All right, and you can now calculate the bias. So I just have to calculate under a fixed theta the expectation of that random variable. If I take the expectation of here, my linearity comes inside. The expectation of xi is just theta. It's the mean of the Gaussian. So I get n values of theta divided by n. I just get theta. All right, so that expectation minus theta here is 0. Okay, so the sample mean is an unbiased estimator of the population mean of the Gaussian. All right, what about the variance? Well, that would just be expectation of theta hat minus its mean, which is theta, because of this equality. And that's just the variance of theta hat. The variance of a sum of IIDs, if I take the variance of this quantity, the scalar becomes 1 over n squared. And then I get the sum I equal 1 to n of the variance of the individuals, because they're all independent. They all have the same variance, which is equal to 1. So I just get n here. I get n over n squared. I get 1 over n. All right, so this is called the parametric rate. The overall risk is going down as 1 over n. All right, it's going it's the variance that has all the risk, because the bias has been set is 0 in this particular case. Other estimators, there's other estimators of this object here. You don't have to use the sample mean by any means. And decision theory tries to say what's better and what's best in some sense. Okay? And all of them turn out to have rate of 1 over n, but they will combine bias and variance in different ways. All right, now it's here that when we do teach these classes, we say this all seems pretty elementary and so on, and it just seems like it leads to lots of calculus down the road, which it does, but there's some depth here. And so there's this James Stein situation, which kind of reveals a little bit of this depth. So James Stein situation is very, it's the kind of the multidimensional version of this. So James Stein estimation. So here I have that x, I get one observation, but it's coming from a Gaussian with mean theta and sigma squared I as the covariance matrix. So these are all vectors now. Okay, let's let them be n-dimensional vectors. Okay, but they're independent because I have an identity covariance matrix. All right. So the game is, having observed x, infer theta. All right, and there's a very natural estimator. Theta hat is equal to, what? Well, the natural estimator here would be x. It's the sample mean of one data point. That seems one way of justifying it. It's also the maximum likely estimator, if you know what maximum likelihood is. Okay. And if you go through the same calculation we just went through over here, you'll see that it has 0 bias and it has variance, which is constant. Right? And so, in fact, if we go back to our plots of risk here, here's theta, and here's the risk. And for these estimators, we're getting some estimators that we should have constant risk everywhere in the space. That seems kind of an appealing property. They're as good anywhere as any other. All right, and this is related to minimax. This is a minimax estimator also because of that property that it's constant everywhere. All right, there's the setup, and now the punchline here is there's another estimator called the James Stein estimator, theta hat, so that's the maximum likelihood estimator, James Stein, which is 1 minus, if I remember the formula, sigma squared over n minus 2 times x. What other, I'm missing a term here, I think. Where's another statistician? Anyway, there's something like this. There's a small, so this is for n greater than or equal to 3. All right, so we don't want 0 there. Okay, so this is just a little number. As n gets larger, it's a smaller and smaller number. So it's basically x, but shrunk a little bit towards the origin. This is called a shrinkage estimator. So it goes a little bit towards the origin. Okay? This is the setup where I assume that sigma squared is known. If you don't know that, you can plug in an estimator for sigma squared, and the story I'm going to tell still goes through. Okay, so this estimator, you can calculate its risk. It's just a little slightly more difficult exercise than what we saw. And you might imagine that around 0, it's going to be a better estimator. All right, because it shrinks the data towards 0. So it's trying to give out the answer of 0. So if the truth were 0, it's got to do better than an estimator which is not trying to move towards 0. Okay, so the risk is going to have to kind of be a little smaller here. All right. And so, but you might think if you push something down somewhere, it'll go up elsewhere. And the amazing fact is it doesn't for n greater than or equal to 3. It basically, the picture is something like this. It goes up in asymptotes. All right, so it never does worse than the naive estimator. And in fact, it's better at some part in the space. And so that has the amazing consequence, which is that the sample mean for the Gaussian is inadmissible. Okay, so by the classical logic, you should throw it out. It's just not a good estimator. There's something else which beats it everywhere in the space. All right. There are many ways to understand this. There's a geometry here. It's basically a geometric fact. And one of the reasons I bring it up is to just introduce this theme, which will permeate throughout the week and the semester, of kind of geometry being a link between statistics and computer science. This is kind of one place you're seeing it. To prove this, it's sort of 2 or 3 pages of integration by parts, and kind of there's an algebraic explanation of it, which is the one most of us know and love. There's also, turns out, a geometric explanation of this, and there's a paper I'm going to refer you to Steve Stigler. If you look on his website and search for James Stein, you'll find this. This has a very beautiful kind of interpretation as a regression problem. If you take a cloud of points, there's many ways to put a line through a cloud of points. One way is to take the cloud of points and put a line through it which minimizes errors in this direction. Another way to take a cloud of points is to put a line through it which minimizes errors in this direction. All right, that turns out to be related to the maximum likelihood estimator, and that's related to the James-Stein estimator. So these lines are slightly different, and they give better or worse risk. And now you can sort of see why you need n greater than or equal to 3. If you just have 2 points, there's only one line in either perspective. So n's got to be greater than or equal to 3 for this phenomenon to kick in. All right, so that's just a little bit on classical decision theory. Let me finish up here by, well, first let me see if there are any questions about that. So that's as slow as I can possibly go, but introducing the notion of risk, bias, variance, and so on. Just one word is, if you ever say the words bias and variance, you're being frequentist. Okay? Most Bayesians are sort of say, well, that's not relevant to us, because that's a variance over other data you could have gotten. I'll say a little more about Bayesian frequentist here in a minute, but that's just, yes?
So, the natural question from a computer science point of view is, are there standard results about lower bounds on the risk you can get for whole classes of estimators? Are there optimality results?
Yeah.
So the classes are...
So there's a huge literature on it,
yeah.
And there's a book by Sasha Tsibakov which kind of lays out many of the tools for finding lower bounds. There's kind of a standard set of tools. They have kind of covering numbers and so on, and finding worst classes of families and so on. There's several such tools, and that book kind of goes through some interesting non-parametric estimators, gets their rate, like we did here. This is a parametric situation, but goes through more interesting estimators, gets their rate in terms of bias and variance, and then shows they're matched by a lower bound, so they're optimal. So there's a huge literature on optimality gotten by finding lower bounds and matching algorithm upper bounds. Tsibakov, and so again, I can do a little better job of giving you references here offline, or I'll send an email. Tsibakov, Alexander Tsibakov has got a book called An Introduction to Non-Parametric Estimation, and that's kind of a very readable little small volume that has all the, goes through the tools for finding lower bounds. Yeah?
I was going to say, maybe for this audience, I imagine the first reaction will be, for parametric,
Yeah.
Always one of the answers, so maybe you can say a bit more about the
Oh, well, in some sense, this is already non-parametric here, just to be clear. The number of, if I write this out as coordinates, this is really xi is equal to theta I plus sigma squared times a IID Gaussian scalar. The number of data points is, this is 1 to n, and the number of parameters are going up together. All right, so that's already what, so in statistics, parametric means the number of parameters is fixed and not growing as you get more data. Non-parametric is not that. It's like nonlinear is not linear. Non-parametric doesn't mean there are no parameters. There are always parameters. It means the number of parameters is growing as you get more data, and you have to tame that growth in some way. So this is already, in some sense, a classical non-parametric setting. But more broadly speaking, non-parametrics comes in when you try to estimate things like functions. So I have I had a cloud of data up there, and I could put a function through that data instead of a linear line, and that function could be allowed to have more and more blips in it as you get more and more data. And you would like to then calculate the risk as you let that growth of that, the number of blips you allow, the smoothness to decrease as you get more and more data. Anyway, there's going to be Martin Wainwright on Wednesday or Thursday, I think, is giving a whole talk on high-dimensional statistics, where there'll be a fair blend of parametric and non-parametric, I think. But yeah, I was just giving examples to introduce vocabulary. The real problems that people have been facing for the last 40 years after Wald were much of them were non-parametric, where the number of parameters is allowed to grow. Any other comments or questions? Yes?
Quick comment. I mean, there's some, I guess, notational differences between various communities.
Yeah.
When you said the variance was constant, actually the dimension, I guess, right?
Oh, always dimension is either hidden or not in all these equations. So,
And also our lower
yeah.
bounds and so on.
Yes.
See is often based on the dimension.
Yes.
Perhaps, your parameters will be different.
Yeah, that's right. Again, I'm going to point to Martin, who's going to have a P or D, whatever he's going to call it, throughout his equations. So dimensionality will be tracked, and you'll try to get rid of log factors and all that, and be very careful about dimension. I'm going to be in the elementary guided this morning, which is not talking very much about that. But yeah, very good point. In fact, the hard analysis, it's usually easy to get an analysis that goes as n, and get the rates and all that in n, and then you hide the D in your big O notation. But the better analyses, and nowadays that's what's mostly required to get published, is to have the D explicit. Let me think about my time here. Let's see. I got I started at 9, right. I think I'm going to skip over the next. I had a couple of slides on more Bayesian frequentists, but I think I'm going to leave the slides available and not do it because I have more material that I want to get to that's a little less philosophical. So let me skip over Bayesian frequentist here. All right, so let me just sort of put this slide up for a second. This is much of the work we'll probably see this semester is frequentist in character. It's the area that has led itself to more analysis, and there's more ties already set up between computation and statistics. Just to be clear, frequentists write down risk functions, and they try to typically break them into pieces, and they try to analyze the pieces and so on. And there's kind of a hierarchy of analytic activity. One of them is just to show that as the number of data points get large, that the estimator you get will converge to the truth. That theta hat should go to theta as n gets large, things like that, and then do that non-parametrically. You want to also typically do better than that and show how fast is it going to the truth, how fast is what's the rate. And then statisticians tend to be more focused on this issue and less on these. Often people in machine learning tend to focus more on these and less on this. There's a little bit of a cultural divide. A statistician is often very interested in the uncertainty, the distribution of the estimator, not just whether it's going to go to the truth and whether it's going to go there fast. Okay, why do you care about the distribution of the estimator? Well, you're typically comparing estimators. You're trying to compare decisions, and you want to know, are they really separate or are they overlapping? If they're overlapping, I want to get more data so I can make them more separate, and so I really care about the sampling distribution. We've already been kind of asked some questions about this. The activity in non-parametrics started with testing. That was in the 60s, and now we've seen it for now about 2 decades in estimating functions and then high-dimensional statistics. And let me also then point to, there's many texts on empirical process theory where it's really the mathematical workhorse of these of the analysis here, where you try to analyze quantities like these approximation and estimation errors, and you get these kind of rates. This is basically uniform convergence theorems of various kinds and uniform distributional theorems. And VC dimension is one of the ideas that kind of started this theory back in 1970, but there were many layers after VC dimension. So a lot of the computer scientists who may know about VC dimension, that's great, but there's many more powerful tools inside of this whole theory of empirical processes. There's big texts on empirical processes that give you a lot of the more modern perspective. And again, I hope Martin will do a little bit of that in his talk. Okay, so all right, so now let me tell you a little bit about a couple of anecdotes, things that we've worked on that give a hint of kind of ways you can do theory in this computation meets statistics domains. One of them will be really kind of in some sense, pure theoretician's effort. That's what this is going to be. That should look somewhat familiar to you, using ideas from convex optimization. And the other is a little different. It's going to be a little more bottom-up, using divide and conquer ideas to try to bring algorithms together with inference and sort of see what's hard and easy. What I like about this part of the talk is that, in some sense, the best principle in all of computation is divide and conquer. You have a hard problem, you break it into simpler pieces, and hopefully you can solve each piece and bring it back together. In statistics, in some sense, that's the opposite. In statistics, it's all about integrating. If you start to average, then things start to happen. Breaking things up from the very beginning seems like the wrong way to go. But that has to be the way to go. You can't solve hard problems without breaking them up into pieces in some generalized sense. So this is kind of real life. We have to face the idea of breaking things up, but still do inferential things. So I think that's an interesting intellectual challenge. Okay, so a bit on this work with Venkat Chandrasekaran, who will be here in the first workshop, talking a bit more about this. We've been looking at convex relaxation as a way to talk about these trade-offs and give an example of a kind of theoretical statement that I alluded to earlier on in a very simplified domain, but showing that it can be done. All right, so to return to some of my earlier themes, in our current state of understanding, it's typically the case you think of more data means more computation. I mean, in classical database theory or computer science in general, it just can't be otherwise. I give you more data points, you have to process each data point, and that costs you something on it. It has to be you. The equations of theory applied to these domains have to show you that you pay more to have more data. All right? But there's another way of thinking about this, the more the statistician way of thinking, which is that when I have more data, I have more inferential strength in my object there. Okay? And so I don't need to touch it less to reveal that strength. I should be able to get by with less computation if I have more strength in my data to make the inferences I care about. All right? And so one kind of concrete way of saying that is that I should be able to use things like laws of large numbers. If in some algorithm there's a sum over many things, I might be able to just replace that with throw in a number, because there's a law of large numbers which tells me what that number should be. And that law will be increasingly good as I get more data, and so and more generally there'll be asymptotic expansions of some kind, which for small amounts of data I'll need the whole expansion, and as I get more and more data I can start throwing away terms and do better and better and better. So there should be algorithmic consequences for the fact that you have more power as you get more of this stuff. All right, and that perspective is just not as widely appreciated as it should be. I think it's going to change over time. There have been other authors who've pointed this out and have been working on this. Here's just some of this. Is not old literature, but the early 2000s. There was a nice paper by Botu and Bousquet. Shalev Schwartz-Shribo have worked on several papers along these lines, pointing these things out. Alec Argawal had a thesis on topics related to this. There's a paper on sparse PCA and approaches to sparse PCA that looks at these trade-offs by Amini and Wainwright. And a nice recent paper by Berkeley and Rigolet looking at lower bound technology to look at these kind of issues. So for the long-term visitors, if you haven't read those papers already, you're going to want to read them. They're a good basic starting place for these looking at these problems. Okay, so the basic setup is going to be that we're going to want to have a notion of runtime, the computer science quantity, and number of samples, the statistics quantity, both on the same plot. There needs to be a third axis, which is the risk, and we're trying to get a trade-off among all three things: risk, number of samples, and runtime. That's the goal. And the way we've made progress on this is to fix the third dimension, fix the risk to a fixed value, say 0.05 if it's an error rate. And so we've made a slice through this three-dimensional surface, and we're going to look at the trade-off that induces between the other two variables, the runtime and the number of samples. All right, so that plot is not often been looked at, but there are parts on it which are well understood. So statistical minimax theory is all about this line here. There is some lower bound on the number of samples you need to solve a problem, irrespective of the procedure. For any procedure, I need at least so many samples to solve the problem at all. That's what minimax theory does, aims to do, and does do. So there are many domains in which this line where it is known, and there are many procedures which are on top of that line or very close to that line. So that line's well understood. I hate to say this in front of a computer science community, but the computer science corresponding line is this one here. It's sort of less well known. All right, these are lower bounds on the runtime for any problem size, for any instance. Okay, so lower bound on the complexity of the problem, irrespective of the problem size. Okay, so we've sort of argued that this is less well understood. I mean, there are some lower bounds in computer science, but they're, at least to my understanding, as much as an active open area, will be for quite some time to try to get lower bounds to be realistic and match known upper bounds. But we're interested not in those regimes. We're interested in these kind of trade-offs where we introduce a trade-off between runtime and number of samples. And we're going to then try to move along that trade-off curve as a tunable parameter for a user, as who's getting more data and is trying to fix the risk, and do so in a certain amount of time. So here's going to be our little analysis domain. This is kind of the Bohr atom of statistics. It's the denoising problem studied by Donahoe and Johnston and many others. So we're going to have a signal, x star, a vector, which is going to live in some set S. For us, this is going to be a complicated set. It'll be a combinatorial set of some kind that will allow us to get interesting classes of procedures. Not a simple set that where the sample mean is the best you can do. And we're going to noise up that signal. We're going to add noise to it, scaled by some sigma. And the noise will be Gaussian for this talk. That assumption can be removed just with a different kind of analysis. That's not essential. All right, so our model is that we get data which is just a noised up version of the original signal, and we want to recover x star. We're going to make an IID assumption to make the analysis easier. So we're going to assume we get IID samples out of this observation model. And we're going to use convex programming as our estimation procedures. Our theta hats or our delta of x are going to be convex optimization. So first thing we're going to do is, because we have IID data, we're just going to take the sample mean. That's known as a sufficient statistic, and we can do just as well by working with that as with the individual data. So our data is going to be now y bar. So our estimator, if we were to optimize over the set S, would be just the minimum over the set S of a loss function. Our loss function is going to be squared error here. So we would take the data minus the estimator, and we want to make that as small as possible. That's a natural estimator. Okay, so it's a optimization problem. For both computational and statistical reasons, you probably don't really want to do this. First of all, this set's going to be complicated. It's probably going to be NP hard or worse to solve that problem. So you would probably relax this into a convex problem for computational reasons, but also for statistical reasons. In the spirit of James Stein, it will turn out it's often useful to shrink problems and make them a little simpler in some way. In that case, shrink towards zero. Here, look at relaxations to bigger sets. And you get better risk. Okay, so for two reasons we want to do this. So the next thing we're going to do is look at a enclosing convex set C and minimize over that to get our estimator. So we'll be calling the estimator x hat indexed by the slightly bigger set that you're working with to optimize. So if this was our original set, say it was discrete here, you might look at its convex hull as a first relaxation, and you would like to optimize over that convex hull. All right, and now we're going to tie into the literature in optimization, which defines hierarchies of these relaxations like Lasserre and so on, to get computational complexity. That's on the computational side of our curve. And we need to get an accompanying statistical complexity so we get an actual trade-off. All right, so to set that up, we need a little bit of convex geometry. Around each point, we can define the cone. So T is the set of directions which, departing from some x star, locally live inside the set C. Okay, so it's a cone. And here's a theorem which relates statistical risk to the geometry of this setup. Okay, so let's be clear here. This is, on the left-hand side, a risk function. Okay, the loss is L2, squared loss. Here's the truth. That was what I was calling theta in the earlier slides. This is what I was calling theta hat or delta of x. We're just taking the difference and squaring. So that's a loss, and there's the risk function. There's the expectation to make this into a risk function. Okay, so with a bit of convex geometry and kind of optimization, theoretic characterization of the solutions, you can write this as being upper bounded by 1 over n times this expectation. There's no data here. This is not a statistical quantity. This is a geometric quantity. So here we have the inner product between a direction delta, which lives in this cone locally around x star, lives also in the L2 ball. Inner product between that and z, where z is the thing which is random, where we take the expectation of. So this is Gaussian. So we're looking at, for each delta, how much the noise kind of aligns with that delta. Okay? And then we take the supremum over all such delta. All right, so if our cone is small, there aren't many directions delta living inside the cone. Here's the deltas. And so the noise is going to, there's going to be perturbations, noise here, z, and the inner product is going to be a certain value. If I let my cone, on the other hand, get larger, I'm going to have more directions delta available to me, and that supremum can only increase. All right, so this is grows monotonically in the size of the cone. Okay. Okay, so why would you let the cone grow? So from a statistical point of view, you're only going to do worse. There's more directions in which the perturbations can screw you up, basically. All right, because on the computational sides, if I let the cone grow, I probably get an object that has a simpler geometry, and I get these relaxations like Lasserre and Shirelli-Adams and so on and so forth. Okay, so we're starting to see a trade-off. All right, now to turn this into a trade-off, actually, what we're going to do is rearrange this equation a little bit. So as I said earlier, we're going to fix the risk to a certain value. Let's fix it to be 1, and just with all its generality. And then, so the left-hand side is now 1, and then rearrange the equation. So to achieve a risk of at most 1, the number of data points has got to be greater than or equal to this geometric quantity. So let's give this thing a name now. We're going to call this the Gaussian squared complexity. It's a complexity depending on a Gaussian variable. It's a Gaussian squared complexity. So if you can calculate this for sets of interest, this will be a number. All right, and so that number scales the ambient noise level, and if you have that many data points, I can guarantee a risk of at most 1. All right, so if I can do this now for nested sets of things, I can start to get an actual trade-off curve. All right, so we're going to do that. Yes?
So this is always a linear change in the data. Like change from n to n squared. Sorry. So the loss here is going from n, say, to 2n or something. Is that right?
Oh, no, as a function of the geometry,
yes, but it's
1 over n.
It's
So yeah, that's right. Okay, so let's now look at these nested C's. So we're going to start with the convex hull as our basic set, but then we're going to look at larger and larger sets, and we're going to follow along Shirley, Adams, Perillo, Serre, et cetera, who have various algebraic and combinatorial relaxations already well studied. Okay, so these things are ordered by computational complexity, and we're going to now add to this a statistical characterization. So let's look at some examples. So I'm going to claim you can calculate these things. It's basically some kind of Gaussian isoperimetry and calculations of convex geometry. So here's an example of doing this. Let's look at the set of cut matrices as our set. So I have an outer product between a Rademacher vector and itself. So a complicated set. If you'd like to optimize over that, you're out of luck. But you can optimize over its convex hull, the cut polytope, and do that in runtime superpolynomial in P. What is P? That's the number of degrees of freedom in my set here. So this is actually a square root P by square root P matrix. There's P elements in my matrix. That's going to be the size of the problem. This column, we're just going to be, in all of these examples, borrowing from the existing literature. So this is the computational column. This will be the statistics column. There's another relaxation, a little bit larger, the elliptope, which has an algorithm running in P to the 1.75. And then there's the nuclear norm ball, of love to many people in the room, where there's an algorithm running at P to the 1.5. So that's all known. Here's what's new. So we calculate the Gaussian square complexity. You can get an analytical result in this case. And it goes as square root of P in all cases. It has to grow. We're getting better computation and worse statistics risks as we go down this column. And it does grow, but only in the constant. All right, so this is kind of a real big data result. It suggests that the algorithms further down here are going to be the better algorithms pretty quickly as you get more and more data. All right, in the computational literature, if you look at approximation ratio as your metric of success, you tend to prefer things up here. These things have bad approximation ratio, but from a statistics point of view, it's quite different. They have good risk as you go down this hierarchy. So you often hear people talking about, the big data regime, simple algorithms are preferred, and this in some sense is a first theoretical characterization of that, or statement of that folk theorem. As another example, let's look at the set of all perfect matchings in a complete graph. That's our set we're trying to infer from. Optimizing over that is hard, so you can relax to a convex hull. There's a runtime of P cubed. You can relax further to the hypersimplex, and the running time is P to the 1.5. And here again, you can calculate the Gaussian square complexity analytically, and it scales, it's constant up to, the only difference is in the constant. And so again, you would prefer the hypersimplex for large data problems in this case. Here's another, it's a sparse PCA or a planted clique kind of problem. We have adjacency matrices of graphs, and we have this clique on square root many nodes. The Kolar is in the room, if I'm not mistaken. So the convex hull, there's a super polynomial algorithm for that. There's the nuclear norm ball, widely studied. And here we see a little bit more of a difference here. It's P to the 1/4 and P to the 1/2 as we go down the statistics hierarchy. So in this case, you might prefer the more complicated algorithm a little further as you get more and more data until you finally switch over to the other one. Last example, because I do have a second part of the talk I want to get to. Banding estimators. I think, again, Bickel and Leviner might be both in the room. The problem here is that I have a huge covariance matrix, and it's and I have very little data. So most of the entries I can't estimate. A typical response has been to band it, to only estimate things around the tri-diagonal, say. Okay. Well, that's fine if you have an ordering of the variables already a priori defined. So, for example, if it's a time series, that would be your ordering, and you would know what band. But if it's like a biological network of some kind, you don't know what the order of the variables are. That's part of the inference problem, is to figure out how to order the variables, and now you can look at these banding estimators. All right, so we have a little stylized version of that where we assume there's a known tri-diagonal matrix where there's a permutation matrix that's unknown, and that's what you're trying to infer. So our set S is the set of permutation matrices, or defined by the set of permutation matrices. Again, it's known what the computation complexity is, and again, we see in this case that inferring that permutation matrix can be done equally well by the cheaper algorithms. All right, so that's our paper. This appears in Proceedings of the National Academy of Sciences earlier this year. It really is a first little foray, an attempt to make a full little theory in a little model world, this kind of Bohr-atom world of denoising. You move outside of denoising, we are not so far able to we have not made that much progress. It's a hard problem, but here we did manage to get some concrete results. So this is kind of our little folk theorem, now becomes a little more of a real theorem. I already talked about a little bit the difference of how you measure how good you're doing. Kind of the computer science answer has been to look at these approximation ratios, and they're misleading for this class of problems. We should be looking at this different object, this risk. And so we want to look back at those kind of hierarchies then to kind of from this new point of view. What hierarchy should we be defining to be able to get tunable curves and that give us good notions of Gaussian squared complexity instead of approximation ratio? All right, so I'm done with that, and I have 20 minutes left, and that's perfect for this last part. Well, let me see if there's a quick question or two on that material. Yeah.
Just something very quick. How sensitive is that result to the assumption of Gaussianity on C?
Almost not at all. So certainly sub-Gaussian analysis, this goes through just fine. And if you don't you put something else in there, heavy-tailed this or that, sub-exponential something, it would just be harder, different math. I think we haven't done enough analysis to say how robust the kind of meta theorem I'm talking about is. But that's kind of the part of the analysis which is easiest to change and to work with. There's other interesting ones which are harder to change. Yes?
Do you have a lower bound?
No. Same reason. I mean, lower bounds would be assuming that in computer science we could do lower bounds in some generality. And we can't, and so we're kind of missing that. But maybe at the end of this semester, that is the open problem, really, is to get joint statistics and computation lower bounds. And in some sufficiently broad, interesting class of problems. That's the...
How would you put an uncertainty measure on algorithms like this?
Uncertainty measure on algorithms? Maybe the bootstrap. Let me move to the bootstrap in the second part. Was there another? I saw another hand. Quickly, yeah.
So I think here we are assuming that you get the data from somewhere, right? So there are...
Get the data from somewhere.
I mean, like someone gives you the data.
Yeah.
Now there are other cases where you actually have to expend some computational cost to
Absolutely.
get more samples.
Yeah,
So
exactly.
There's
That's
a
right.
trade-off. Do you expend that cost to get more samples?
Absolutely.
Do you have a fancier...
Yeah, no, you're right. So that's called either experimental design or optimal experimental design or active learning in many literatures, and you probably have many other names for it. You're absolutely right. We're talking about 4 parameters here, really. Risk, number of samples, runtime, and P, the number of dimensions, which I wasn't so explicit about, but it crept in. You're absolutely right. There should be other dimensions. We get a fuller trade-off. How costly is it to get an example, and how costly is, the decisions themselves have consequences. I want to put the cost, utility. We need economics, right? But at some point, you've got to kind of define your domain and carve it out a little bit. That's what we've done. Okay. All right, so let's talk about the bootstrap. So let me again acknowledge colleagues here, Ariel Kleiner. These are all people working with me here at Berkeley. Ariel Purna-Sarkar and Amit Talwalkar. Ariel, I want to particularly recognize as being a leader on this project. So the bootstrap, let me just ask how many people of you already know what the bootstrap is? Okay, good. About a third, but it's kind of surprising. It's like if I ask how many of you know what the FFT is, everybody. How many of you know, et cetera, linear programming, everybody. So the big idea in many operations research, the big idea in linear algebra or signal processing, everyone knows. The big idea in statistics is maybe the bootstrap. It's one of the top 5 big ideas, but it's amazing how unwidely known it is. And in fact, part of the problem is that there's been this parallel development of this literature called machine learning or data mining or whatever you want to call it, which is really just statistics with using some kind of different language and working on different classes of problems. It's not a new field. It's a collection of topics in an old field of statistical inference and decision making. That field has focused for various reasons, not so much on uncertainty in outputs of algorithms, but just on the algorithm themselves and the output. I got a classifier. I take in a vector and I want to say yes or no, 1 or 0, that's the output. And I'm often not asking, are you sure about that 1 and 0? Or if I'm giving out a real value, 0.7, that's your probability of having the disease. I want to say, well, how sure are you of that probability? All right, and so in statistics, the concern is often more about that, how sure you are, and not so much just about the number itself. All right, so I want to spend some time on the bootstrap and then talk about the computational side of the bootstrap to drive this point home, that we should be also worried about error bars and not just about optimization procedures in particular that take in data and give out an answer. There should be an error bar around the answer. And how do we get error bars? And maybe to belabor this for a second, so suppose I'm just trying to get the mean height of people, and I have a sample here, a couple hundred people. I take each of your heights and I can take the sample mean as my estimator. So it turns out the mean height is 6 feet, say. But how sure am I of that 6 feet? Am I really to bet on the next person coming in the door being 6 feet? Well, I need an error bar. And you may know that for the sample mean, there is an error bar. It's called the standard error of the mean. It's a little formula. You can calculate it, and it goes as 1 over square root of the number of people in the room, the number of people I measured. Okay? What if instead I use the median as my estimator? The sample means, not robust, and I know the median might be better. So I use the median, and it came out to be, 5 foot 9 inches or something. I would say, well, what's your error bar? I want to know how sure you are of this, because I want to make a decision based on that. I've got to build my doors a certain height based on your analysis. And you say, well, there is no formula. I don't really know. In fact, there isn't. There isn't a formula for the error bar of the median. All right, so how do you get the uncertainty of the error of the median? Well, here's a way. Suppose I have 100 people in my data. I calculate the median by sorting and finding anything in the middle, roughly speaking. There's faster ways to do it, but that's one way. Now take those 100 data points and sample from them with replacement and get another new 100 data points. Some of the same old data points will appear in your resampled data set and some will not appear. Okay? Sort those and find the thing in the middle. I get a sample median of that resampled data set. Now do that a couple hundred times. For each resampled data set, you'll get a different median. It'll fluctuate around. All right? And those fluctuations actually are the sampling distribution of the median. Okay? If you were to take some measure of spread of those things and return them to me as an error bar, that's a correct error bar, in the sense that the true underlying population will lie inside of your error bar the advertised fraction of times, 95% or whatever you calculated. All right, so that's the bootstrap. Now, if you replace median with some other optimization procedure you like or whatever, you just resample the data with replacement a few hundred times, calculate your procedure, your black box on whatever, on those resampled data sets. You get fluctuations in your estimator, and now give me a notion of spread. That is an error bar. It's almost by definition an error bar. All right, now, so why did I find this interesting? Well, many reasons, but one of them is that it's totally parallelizable. I have a big data set sitting here. I 200 times say resample replacement. I could do that separately on 200 separate computers in my cloud computer. Each one of them calculates locally its median or whatever, black box, and returns that to home, and I get the spread I get the fluctuations, and I have an error bar. So when cloud computers started coming around and I was thinking about big data, this seemed like a match made in heaven. We can do the bootstrap on cloud computers. All right? And that's not going to be quite the right story, but that's part of the motivation. Yeah?
Is there an issue of bias here? In some sense...
Yeah, so all estimators have bias and variance, and a bootstrap is an estimator. So you can calculate the bias and variance of the bootstrap. It's kind of a layer on top of the classical analysis, but you can do it, and it's been done. But of course, it depends on the particular problem domain you're in. But that's been done in many problem domains. Yeah.
So if I have a lot of data, can I just split my data into many?
Good question. So that's what I'm going to be getting into. What happens if you have a lot of data? The problem is you're in trouble, and we're going to fix that. Okay. All right. So we have data x1 through xn. Let's form an estimate of some kind. Let's call it now theta n. I probably should put a hat there. I neglected to do that. It's just some function of the data, and again, it doesn't have to be a literal parameter. It could be a function you're estimating or a measure or something else. And I'm not interested in that algorithm that does that, like I was in the first part of the talk. Now I'm interested in some notion of the quality of the estimate. All right, error bars or confidence intervals or bias or variance. I might be trying to estimate the bias and variance. Those are estimates of quality. All right, so the ideal frequentist would do the following. The ideal frequentist would say, well, I'm going to get multiple data sets. Instead of just having one data set, let's imagine I had many data sets of the same size. All right? If I did that, I could, for each data set, compute my estimator on them, and now I get a notion of fluctuations, and that is a notion that's called the sampling distribution, if I had multiple data sets. I'm really doing that frequentist averaging, that expectation of theta when I have multiple data sets. I'm getting samples from my sample space. But you only have one data set of size n. You can't do that. So it seems like you're stuck. But you're not. So the first thing you remember is that the data came from somewhere. It's a data set, but there was an underlying population which can generate any data points. It's usually continuous because any data can arise. And imagine the supreme being up in heaven has that population and sent down to us a data set that says n. All right? Now, but the supreme being has the whole population, can generate any data, and so could sample multiple data sets from the population. So the supreme being could be the ideal frequentist. And the supreme being's computer would look like the following. They would take the population, sample one data set, two data sets, m data sets, and this would be done on the supreme being's cloud computer because it's totally parallelizable. And then this would come in, you'd calculate the estimators, you put this into some notion of spread, and you would have, with your cloud computer, computed the error bar. All right, that's what the supreme mean has. On Earth, we just got one data set of size n. All right, but here's the important, totally trivial, but important trick. Think of that not as a data set of size n. Think of it as to form, say, a histogram. Okay, histogram is itself it's a distribution. It's a measure. Okay, it's a probability measure. It's discrete. It puts mass only on discrete points, but it itself is a probability measure. It integrates to 1 and it's positive. All right, as a probability measure, you can generate data from it. Okay, that's conceptually an important point. Right? You can generate as many data points as you want. You can generate one data point from it, and then what that would be is taking the original data and sampling from the original data. Okay? You could generate multiple data points from it, and what that would be is taking the original data and sampling with replacement. It's exactly the same concept. All right, now, the next critical point is to note that the empirical distribution, that's what it's, empirical measure, empirical distribution, is a good approximation of the underlying population with high probability uniformly. There's many theorems that state this. Okay? All right, and that's true for uniformly. So for any underlying probability distribution, the empirical will be a good approximation to it as n gets large. All right, so now the next step is to forget that there was a supreme being that generated the data. This is now the population. All right, it is a measure. It can generate as many data points as you want. It can do it multiple times. All right. So now you're a supreme being in the world in which that's the population.
Quick question. You mean a uniform distribution on the data, on the empirical data, right? Or
Well, this empirical, so there could have been, the same point could have occurred multiple times in the original data set.
Yeah.
Because that's why we get this bar
On the
that's a little bit
multi-set.
higher. Yeah, or we aggregate, or we got our bin size a little bit bigger and we got multiple data points at the same point. Yeah. But we're taking a sampling of the original data with replacement. That's what we're doing when we're sampling from the histogram based on the data. Same concept. All right, so now you're in a world where you're the supreme being and that's the population. So now you do go through the same diagram as we had before, where we take the data now. In fact, I should have put a little histogram here. And now you sample from that on your cloud computer on Earth. You sample one data set from the empirical, and you get it here. And I put a star here to note these resamplings. These will be different because they're sampling with replacement. There's been noise added. Okay? They will give you different values of the estimators, and you can plug them into the same formula as before that the supreme mean is used to get a notion of fluctuation, quality. All right? An amazing theory that's been developed for this is that this is correct. In fact, so intuitively it should be correct because all these operators are the same as the supreme beings, and the only approximation was replacing a certain distribution with its approximation here, and that's with high probability uniformly a good approximation. So if all these operators are continuous in some functional sense, then this should be correct. And so that's the theory, basically. There's books on making that theory precise, but that's the theory. Okay. All right, but what about the big data issue? Yeah.
I was just going to ask, if the data are actually not discrete, so you're getting
Yeah.
500 numbers from a real number line.
Yeah.
How do you do a sample with replacement when the next time that data could flow in could actually be in between the discrete values?
No, you sample from replacement from your original data. You're not sampling from future data. You're just taking original data. You get a measure that happens to be discrete, and you're sampling from that. There's also something called a smoothed bootstrap, though, which is perfectly fine, too, which you take your original histogram and you smooth it and get a real, honest to God, density that can give you real numbers. That's not in the original data. And I think that's even less scalable than the bootstrap. So for computational reasons, I wouldn't do that. But as a theory exercise, it's been done, and it's a good idea. Okay, anyway, now let's go back to the real. It seems to be a wonderful match to modern distributed computing, but the number of when you resample a data with replacement, you get 0.632 of the original data appearing. So if this is a terabyte, we get 632 gigabytes. So we go back to our little plot here of our cloud computer. On each one of these arrows, we're sending 632 gigabytes, and we're doing that 200 times. That's going to flood the network. That's not going to work. Okay, so we're kind of stuck. We can't do the bootstrap on a terabyte naively. I mean, if you think about it and make, do really good routers and think about hierarchical, blah, 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 you might be able to engineer it, but it would take a lot of time. It's not kind of easy. Okay, so here's another way of thinking about the problem. It's called subsampling, developed by Politis, Romano, and Wolf. It was developed for theoretical reasons, not for practical reasons, but it has a kind of practical consequence. So the idea is you take you imagine your population, you take your data size n, and then you subsample a subsample size b. So think of this as kind of roughly, say, square root of n, much smaller. All right, now you apply your estimator to that. All right, now you can do this many times because there's n choose b numbers of ways of choosing subsamples. So you can do this many times, and you can get many values of your estimator. So you can get fluctuations in your estimator in this way from one data set. Now, there's a problem, which is that these fluctuations are on a different scale. They're on the scale B. They're applied to data of size B. It's a smaller data set, so the fluctuations will be bigger. You'll get artificially big error bars. All right? Now, if you're thinking of kind of approximation kind of person, you sort of say, well, this might not matter in some limits and all. But if you're thinking of statistical error bars, it really matters. It's all, you're trying to get the error bar to be correct. If the error bar is scaled wrong, it's just wrong. Right? So the people who proposed this were aware of this, of course, and what they said, well, is that you have to, because the error bar is on the wrong scale, you have to analytically correct the error bars. They're too big, so you multiply them by a square root of, say, b over n, when the estimator is a square root style estimator, when the uncertainty is fluctuating on the square root scale. If the estimator is not square, you wouldn't necessarily know. You have to do the analysis. All right, so this kind of approach has a bit of an analytical headache. You have to kind of figure out how to scale analytically, and that's not been done for many estimators and wouldn't be easy in practice necessarily. There's another problem, which arises when you look at actual experiments.
For the L2 thing, it's the root B over n, but for
Yeah.
other estimator, you don't know what it is.
For other estimators, you wouldn't know what it is. Maybe it's cube root or something you wouldn't know. All right, let's look at an actual experiment using subsampling. So here, this is going to be a little synthetic data, 50,000 data points. The covariance, the predictor space is a 100-dimensional vector, 100-dimensional space. We're doing linear regression. We're going to have student t of variables as our x-coordinates, and we're going to do least squares to fit. It's just classical linear regression. All right, but it was synthetic data, so we can calculate the true error bar, and we can calculate the estimated error bar, and we can compare it, get a relative error bar. And here's the key statement. We're going to now take the number of samples to grow as a power law, n to the gamma, where gamma goes between 1/2 and 1. 1/2 would be very ambitious subsampling, and 1 is no subsampling. All right, and here are some examples. Here's, as a function of algorithmic time, this thing is running, subsampling away on a computer or resampling away. Here's the relative error. It should go down, but it won't go to 0 because the number of data points is held fixed. Here's the bootstrap, so it comes down pretty quickly and stabilizes. Here's subsampling for n to the 0.5, very aggressive, and it's failing. It's just giving you the wrong error bar. 6, it's still failing. 7 and 8, it's actually beating the bootstrap in a computational sense. It's getting the same answer and doing it more quickly on a single computer. 0.9, it's now again failing, unfortunately. So there's a range of this tuning parameter, the gamma, where it works, and outside of that it fails. And the problem is that gamma is problem dependent. Okay, so this makes me hesitate. We were thinking of implementing this with our colleagues doing bootstrap on databases, and that gave us pause. Okay, so we worked out a new idea called the bag of little bootstraps. That is both subsampling and bootstrap together, and it does scale. So it's going to kind of somehow put the two ideas together. It's parallelizable, so it's appropriate for distributed computers, and it doesn't require any analytical rescaling. All right, I've got just a few more minutes, but it's actually really easy to describe this idea. So let's go back to this picture here. Here's the supreme mean. Here's our data set on Earth. And a subsampling person would take this data set and subsample it. Okay? Very natural in the big data world to subsample. How else can you make progress? All right? So now ignore the fact that these B points came through an intermediate stage. Those points are themselves a sample from the population. Okay? Who cares that they came through an intermediate stage? They're a random sample from the population. So for the same uniform convergence results, they're a good approximation of the population. Now it looks terrible here because I have 10 points on my little stupid slide, but with terabytes and gigabytes, this will also be a pretty good but still noisier approximation of the population in the original histogram. All right, nonetheless, this is a good approximation of the population. So forget that there was a population, and now you're living in a world in which that's the true distribution. Now you can sample, it's a measure, you can sample from that distribution, and you can sample as many times as you want. You don't need to sample B times, even though it was based on B points. You can sample 1 time or 2 or n times. And that's the key, is you can sample from that object n times, and now you're on the correct scale of the original data. And you're getting fluctuations over data sets of size n because you're sampling from this approximation of the population n times. You're getting multiple data sets of size n. The fluctuations over that are already on the right scale. They don't need to be corrected analytically. All right. That is the whole idea. All right. Let me now elaborate a little bit. So what you're doing is you're taking this subsample and you're bootstrapping it, sampling from it n times with replacement instead of b. Now, how would you actually implement that? You wouldn't stupidly take this little small data set of size b and create a big data set of size n, a terabyte. You would keep your b points and have a little counter next to them. How many times did they get resampled in this particular subsample? Sorry. How many times did they get resampled in this resample? All right. Having done all that, you've now got fluctuations in some estimator, and you have an error bar. And it's actually a correct error bar at that point. It's not wrong scale. But it's noisy because it was based on one subsample. But now do the whole procedure again and do it in parallel on your cloud computer. Take multiple subsamples, and for each one of them, bootstrap the subsample. All right, so I have a picture that I think makes it easiest. It's a double nested procedure. It takes the original data, subsample. So if this is a terabyte, this is maybe a few gigabytes. It's not hundreds of gigabytes. It's a few gigabytes that arrive here. Now bootstrap that subsample, and the way you do that is you create multiple resamplings, and again you're sending small numbers of gigabytes along each one of these lines, and then similarly here. Also, streaming operators could be usefully employed here, where you stream all these things and you're never storing anything in these cases. You get now a perfectly good error bar, but now you do it in parallel many times. The noise in those error bars will be canceled by an averaging operator at the end of the day. All right, so let me show you an experiment that, the same experiment as before. Here's the bootstrap, just like before, coming down. Here's the new procedure, BLB, for various values of that exponent, and you can see that it's succeeding for all values of the exponent, between 0.5 and 1 in this case. And it's actually computationally more efficient than the bootstrap on a single computer. All right, but now my last slide is, what if we now do this on a real parallel computer like we promised? This is all sequential, what happens on a real parallel computer. So this experiment was done with a quarter terabyte of data. It was a logistic regression, and it was done with a Newton method, sort of fast method for fitting logistic regression. And our procedure is totally parallelizable, and I'm going to show you the runtime and the accuracy. We've got to compare it to something, so what do we compare to? I told you the bootstrap can't be done on these big-scale problems, and that's never entirely true, so there is a way to think about doing the bootstrap, and I'm going to show you the curve here while I talk. So what we did to implement a bootstrap on this scale is that we took logistic regression, it's an optimization procedure, and we parallelized that. So our cloud computer is now running with one data set, a parallel version of logistic regression. Okay, it takes quite a bit of time, I think thousands of seconds to do that for one iteration. And now we do the resampling process sequentially. We take one resample, give it out to our cloud computer, it runs logistic regression. We resample again by our central computer, and we do it again, and we do it again. So it's a sequential use of our parallel computer. And here's the curve you get by doing that. The bootstrap comes down in relative error. And here's 15,000 seconds. It's starting to stabilize, but it's going to take quite a bit more for it to really get its ultimate answer. Okay, the new procedure instead runs logistic regression, but on these small data sets, not on a quarter terabyte. It's never seen a quarter terabyte. It's seen small numbers of gigabytes on the cloud computer. And here's its runtime. It finishes in, I think that's about 500 seconds. And its accuracy is better than the bootstrap, even after 15,000 seconds. So this is orders of magnitude improvement, the new procedure. It's kind of a new way of organizing error bar calculation. It really does scale. That's a quarter terabyte. And this was not optimized technology. This was running on the Spark infrastructure in the AMP lab, but otherwise not optimized. So I think this kind of thing is going to happen a lot. There's a classical statistical procedure that no one ever thought about the computational issues associated with it. If you rethink it and reorganize it in some way, you can have curves going from here down to here. But it's not going to just happen by magic, by magic. All right, so I'm finished. I went over time a little bit. I want to try to set a good example for the week by finishing quickly here. So there is we have a paper on this in which there's a theory section in which we prove consistency and rates of convergence. There's not anything particularly novel about the theory. We just borrowed existing theory and adapted it to our end. So let me just actually skip it, and if you're interested, you can see the results. At the end of the day, I guess the one take-home of the theory is the other reason that people love the bootstrap is because it beats the central limit theorem. The central limit theorem, its accuracy, of course the central limit theorem is itself an approximation, its accuracy goes as 1 over the square root of the number of data points. The bootstrap error bars are noisy, and as it was asked before, they have a bias and variance. Their bias and variance, i.e. their accuracy, goes as 1 over n, not 1 over square root n. So it's actually viewed as, it beats the central limit theorem. And turns out the new procedure still preserves, this is called higher order correctness. It preserves the higher order correctness. It also has an accuracy of 1 over n, not 1 over square root n. All right, so I'm done. The main take home I wanted to emphasize in this first talk was that, from my point of view, this big data area raises many conceptual challenges. It's often viewed as a systems problem. How do you build a big data processing system? How do you do MapReduce, Hadoop, and so on and so forth? If you see all the conferences advertised about it, that's what it's mainly about. But I think for this audience, I want to emphasize the notion that there's deep issues in integration of inferential and computational thinking, which have only started to be tackled, which our generation, especially the younger people in the room, are poised to tackle. And brand new theories going to come out of this, new perspectives, as well as having impact on the real world, on real data analysis. So I'll finish there and I'll stay. I guess we're starting again in 25 minutes. But let me see if there are any follow-up questions, and I'll stay around the entire time if there are other questions offline. Yeah.
So the convergence rate for the bootstrap, the same types of problems that is linear